on the exploration of Pluto and the Kuiper Belt by New Horizons. I'm Ralph McNutt of the Applied Physics Laboratory, and I'm here to introduce Hal Weaver, who is also at the lab. Hal's the project scientist for New Horizons. He's also a co-investigator on the UV experiment on the Rosetta mission, and so he does double duty like a lot of us in this business. Hal's been an observer for a long time. He actually was the person that definitively identified water in Halley's Comet and in comets in general with the Kuiper Airborne Observatory back in the mid-'80s. He's worked with looking at UV spectra of comets with the IUE satellite, FUSE, and the Hubble Space Telescope. He was instrumental in watching doing the science analysis for the collision of Comet Shoemaker-Levy 9 with Jupiter. And he's been involved with the discoveries during the New Horizons mission with all of the satellites of Pluto that have actually been discovered during the time that the mission has been ongoing. So what we're going to do is to go ahead and have Hal talk about this. We'll have some time for some questions. There's some microphones out on the center here, and we're going to try to bring this to a close fairly promptly at about 6:30 because we've got the culture event that's going on tonight. And so with no more ado, let me introduce Dr. Hal Weaver.
Thank you very much, Ralph. Hola, buenos dias, everyone. Before I start, I just wanted to thank our organizers for inviting me to give this presentation on New Horizons and to the International Astronautics Federation for awarding the New Horizons team the Laurels Award for team achievement. Very much appreciated. So it was just a little over a year ago that the New Horizons spacecraft passed just 12,500 kilometers above the surface of Pluto on July the 14th, 2015. And in this cover slide here, you see an artist view of the New Horizons spacecraft. But this is a real image from the New Horizons spacecraft just after a little while after we pass by Pluto and then are looking back with the sun into the page there. And when you see an image like this, I was just filled with awe and wonder when this came across my computer screen in early September. And we were very surprised by the diversity of Pluto's surface, and in fact, the diversity within the Pluto system. And that's what I'll be telling you about today. But before I get into that, let me give a little bit of background for some perspective on the mission and the motivation for it. This is the initial reconnaissance of this whole new region of the solar system that was only discovered in the early 1990s that we now call the Kuiper Belt. And this is just a cartoon of the solar system showing this white cloud, torus-shaped region, donut-shaped region surrounding the sun called the Kuiper Belt. The first Kuiper Belt object was discovered in 1992, or so we thought, but in fact the first Kuiper Belt object was discovered in 1930 because that was Pluto. But Pluto stood out like a sore thumb for a long time, and I'll get into more of that in just a minute. But the mission, the New Horizons mission, is the first exploration of this whole new zone of the solar system, the third zone. You got the first zone comprised of the rocky, relatively small inner planets, Mercury, Venus, Earth, and Mars. You step out into the second zone, into the realm of the giant planets, Jupiter, Saturn, Uranus, and Neptune. But in fact, the most populated region of the solar system is the Kuiper Belt, with all of these primordial leftovers from the formation and evolution of the solar system. The New Horizons mission, the principal investigator is Alan Stern from the Southwest Research Institute. He apologizes that he couldn't be here himself today to give this presentation, but he is a principal investigator on an instrument on Rosetta, and he is on his way to Darmstadt now for the landing of the orbiter, the Rosetta orbiter, on the surface of Comet Churyumov-Gerasimenko tomorrow morning. So I'm standing in for him. The New Horizons mission is the first of NASA's New Frontiers missions. We actually were approved just before the New Frontiers line was introduced at NASA. These are the mid-size missions, one step up in complexity and scope and amount of money involved relative to Discovery. The small missions in the planetary division of NASA. This is the next step up in between and just below the flagship missions like Cassini. And so we're paving the way for this new class of missions, PI-led, and that's the thing that distinguishes that from a flagship mission. The project manager for the New Horizons mission at the time of the Pluto encounter is Glenn Fountain from APL. APL does the project management for the New Horizons mission. Prior to Glenn, Tom Coughlin was the program manager, and Helene Winters at APL is the program manager now. But the New Horizons spacecraft was launched in January of 2006, and even though it was the fastest spacecraft ever to leave the Earth, it takes a long time to get all the way out to Pluto. We passed Jupiter in February of 2007 and finally reached our target in July of last summer. Okay, the Kuiper Belt. This is a view looking down on the plane of the solar system, and this is not a cartoon. These are showing you the actual positions as of the middle of July of every single known object in the solar system. The Kuiper Belt objects are these little yellow dots, okay, and they're preferentially in the plane of the solar system, but they also extend above and beyond. Pluto's orbit is that purple ellipse, and this is what we knew early on. Shortly after Pluto was discovered, it was unlike any of the other planets in the solar system. It had a highly elongated orbit with an eccentricity of about 0.25, had an inclination to the ecliptic plane. Its orbit had an inclination of about 17 degrees. So very, very different from everything else in the solar system. But once in 1992, the next Kuiper Belt object was discovered, 1992 QB1 by Dave Jewett and Jane Liu. From that point on, there was just an avalanche of new discoveries as we realized that Pluto was only the tip of the iceberg. And we now know of a couple of thousand objects in the Kuiper Belt, and those are all plotted here. And the light bulbs then went off that Pluto no longer stood out like a sore thumb. It was just a typical member of the Kuiper Belt. Now, this is looking, like I say, down on the plane of the solar system. If you now look at it from the side, you'll see what I was talking about in terms of the inclination of Pluto's orbit and that little torus-shaped belt of objects, small, icy dwarf planetesimals, essentially, that form the Kuiper Belt. All of those caret-shaped symbols are comets. Most of the ones that you see here are the ones coming from the Oort cloud, so they have very, very high inclinations. You'll see comet Hale-Bopp here, almost perpendicular, coming in almost perpendicular to the ecliptic plane, the plane of the solar system. But the discovery of the Kuiper Belt really, it truly did revolutionize our view of the formation and evolution of the solar system. When I went to school, we were taught that all of the planets in the solar system basically have been where they are now since the time of their formation 4.6 billion years ago. But the discovery of the Kuiper Belt, and in particular, discovery that there are at least 3 different families, dynamical families of objects in the Kuiper Belt. In order to explain that, it turns out that you need to have extensive radial migration of the giant planets during the early stages of the solar system's formation. So it's only been in this last 25 years that we have a completely different view of the solar system's formation. It's not that staid place where everything was in circular orbit around the sun, but there was a lot of action going on, a lot of motion. We now think that Jupiter may have come in as far towards the sun as almost into Mars's orbit and then moved back out again. And because of that radial migration, it really stirred things up in the solar system. And we think that maybe even Uranus and Neptune flipped spots, okay? And it produced this outer region of planetesimals that we now call the Kuiper Belt. And it was discovery of the Kuiper Belt and the need to explain the architecture of the Kuiper Belt that motivated all of these new models of how the solar system formed and evolved. So that's the motivation for the New Horizons mission. We've never had a spacecraft that's actually gone by an object in the Kuiper Belt. Of course, we've had the Voyagers and the Pioneers that have gone beyond Pluto into the heliosphere, but not near one of these Kuiper Belt objects. So Pluto is the gatekeeper to the Kuiper Belt. It's the brightest and the largest. Despite the discovery of Eris, Pluto is actually slightly larger than Eris. Eris is the one that generated all the controversy about whether or not Pluto is a planet. Pluto, turns out, it is bigger, but just slightly. Eris is more massive. But independent of that, I think that from what you see today, that most of the people on the New Horizons team still consider Pluto a planet, and that's because geologically it looks like a planet, not like one of the smaller objects of the solar system, the asteroids. Okay, so New Horizons, just a little bit about the spacecraft and the instruments. It has 7 instruments. The spacecraft, the largest single structure is this radio antenna, which is 2.1 meters across. So that kind of sets a scale for the spacecraft. It's about the size of a baby grand piano. We have color cameras and an infrared spectral imager. And both of those are in this instrument that we call Ralph. The Alice instrument is an ultraviolet spectrograph. Our highest resolution camera is just panchromatic, it's not color. The long-range reconnaissance imager, LORI. The antenna here is part of a radio experiment called REX, a very interesting experiment that I'll tell you about in a few minutes. We have 2 in situ plasma sensing instruments, the solar wind at Pluto, SWAP, and then PEPSI. Ralph Magnet is the PI of the PEPSI instrument. SWAP is looking at the solar wind and generally lower energy lower energy charged particles from a few hundred eV up to several hundred keV, and then the PEPSI instrument covers higher energy ions all the way out to MeV. This New Horizons mission had a unique experiment that hadn't been carried on an interplanetary spacecraft before, and that's a student-designed and built instrument, the student dust counter, the Venetia Burney student dust counter. Students at the University of Colorado in Boulder designed and built that instrument, and it's a dust counter. Under the direction of the PI is actually Mihai Horanyi at the University of Colorado in Boulder, but it's a bunch of polyvinyl chloride panels, 12 of them, underneath the spacecraft in the ram direction of the spacecraft that count impacts with dust particles as the New Horizons spacecraft passes through the solar system. And once it got past Saturn, these were unique measurements, and the students just did a wonderful job. The power for the spacecraft is provided by a radioisotope thermoelectric generator, an RTG, that was a spare from the Cassini mission. And that's here, the thing that looks like a little bit like a hair curler back there. Now, a couple of remarkable things about the payload for New Horizons. All of the instruments together weigh less than 30 kilograms and draw less than 30 watts. including turn-on surges, okay? And we needed that. We needed them to be low mass, low power in order to enable this mission, because we're heading all the way out to beyond 30 AU from the sun. There's, of course, no possibility of getting solar panels that work out that far, so we needed RTGs. But in order to have enough launch energy to get a spacecraft there in a reasonable amount of time, we had to lightweight everything as much as possible. The RTG started out with a power available of about 240 watts. By the time we got to Pluto, it was down to about 200 watts. But that was plenty to run all of the instruments and to execute the encounter. Okay, since this is an aeronautics conference, I have to show this. This is the launch of New Horizons on January the 19th, 2006. And if you could start the slide for me,
3,
please.
2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a
You can see the 5 solid rocket boosters around the core engine. We also had a Centaur upper stage and a Boeing Star 48 third stage.
Climbs away from Florida's east coast.
We needed the maximum lift capability available in the United States, and that was this configuration.
On its way to
And
the
it was a
very edge of
perfect
our
launch. We were over the Indian Ocean in 45 minutes. We were at the orbit of the moon in only 9 hours. Okay, so we took off at 2 p.m. By 11 p.m., we had already crossed the orbit of the moon. It took the Apollo astronauts 3 days to get there. And so it was the fastest spacecraft ever to leave the Earth. It passed by the orbit of Mars in April of 2006. We got to Jupiter in late February of 2007, just 13 months after launch. Of course, it took Galileo about 5 years to get there. But at Jupiter, we had a great opportunity to have a test run. This was a flyby. We actually the purpose of flying near Jupiter was to get a gravity assist. By going just behind Jupiter, we stole momentum from Jupiter, increased the speed of the spacecraft by 20%, and cut over 3 years from the travel time to Pluto. So if we didn't have that, we'd still be flying out to Pluto now. But not only did we get that gravity assist, we got it close enough to Jupiter that we did a lot of science and got to practice a flyby. And we learned some things from that, but we also got a lot of great science, including just happening to catch Io. You see one of the Galilean satellites, Io, here. This is the best view ever of a terrestrial volcano. Io is the most volcanic object in the solar system. And the volcano was going off, and you could see the plume, Tavashtar plume, in great detail. We could map the trajectory of the particles as they went up several thousand kilometers and then fell back onto the surface. So that was exciting itself. But we continued on, finally reaching the Pluto system in July of last year. This is just a little view of the trajectory of the spacecraft as it went through the Pluto system. This is the spacecraft trajectory here. The sun is over to the right, as is the Earth, and as viewed from Pluto, the sun and the Earth are only about 0.25 degrees an angle from each other. So we flew. One of the important mission design criteria was to fly through the center of the shadow of Pluto, because that enabled a couple of experiments. One was, using that radio experiment, as the spacecraft flew behind Pluto, the antenna, that big antenna, the 2.1 meter, was pointed back at the Earth, and the Deep Space Network, NASA's Deep Space Network, was radiating 80 kilowatts of power from 4 different antennas up to the spacecraft. And by watching the phase change of the radio waves as they pass through Pluto's lower atmosphere, we could measure the mean molecular weight and the thermal structure of Pluto's atmosphere all the way down to the surface. And this is something that had never been done before. But simultaneously with that, we could also use the ultraviolet spectrograph and look at the sun at the same time. And by looking at absorption of sunlight as we pass through Pluto's upper atmosphere and the absorption of molecules and atoms in Pluto's upper atmosphere, we can measure the composition of Pluto's upper atmosphere to much higher precision and looking for new species that had never been seen before. So those were two unique experiments that were enabled by this particular trajectory. And we also tried to go through Sharon, Pluto's largest moon's shadow, but we couldn't go diametrically through the center of it. But we went through part of it, part of the shadow. Okay, so this is what really most of the most exciting stuff, as you can imagine, is taken right near closest approach. The one of the animation groups at JPL produced this animation that's called Eyes on the Solar System. They do this for lots of different missions, but they took our actual sequence from New Horizons, what we actually flew from Pluto minus 7 hours through P plus 1 hour, and showing you everything here in highly compressed form. You see it magnified up here, and the different instruments that are being shown are, that are being used are highlighted up here. But you can see it was of course, we were trying to squeeze as much as we possibly could out of those last several hours. We squeezed basically every single second that we could make observations, we did. Okay, now, a laundry list of things that we wanted to do at Pluto that was determined by various NASA committees in the 1990s. You can really summarize the most basic high-level objectives of the mission with just 3 bullets here. Because we've never been out into the Kuiper Belt, the most important things are, first of all, what do those objects look like? Characterize the geology of both Pluto and Sharon. What are their surfaces made of? And because we know Pluto has an atmosphere, we wanted to study the atmosphere. And then there's a whole list of very specific measurement objectives that drove the design of the instruments on the New Horizons spacecraft, but just at a very high level, this is what we were trying to do. And just to remind you, when the mission was accepted in November of 2001, we only knew about 2 objects in the Pluto system. Pluto itself was discovered in 1930. The largest moon, Sharon, wasn't discovered until 1978. Okay, and that was Sharon. Once the mission was accepted, Alan Stern came to me. I'd done a lot of observations with the Hubble Space Telescope and said, look, there's no reason why Pluto couldn't have other satellites, so we should go out and take inventory of the Pluto system with the best available facility, which is the Hubble Space Telescope. And so we went out and did that. In May of 2005, we discovered 2 new small moons around Pluto. They're now called Nix and Hydra. And then in 2011, we did some other observations with Hubble, discovered Kerberos, and finally in 2012, discovered yet another one, a 4th small satellite called Styx. And remarkably, this is a little cartoon showing you the orbits around the Pluto barycenter of the satellite system. All of them are in the same plane. They're all in almost perfectly circular orbits. And all 4 satellites, the small satellites, are almost in a mean motion resonance with Sharon. This kind of screams out at you that the whole system was created in a single giant impact event when 2 roughly Pluto-sized objects had a glancing collision, and then in the aftermath, you formed a disk, and within that disk, the satellites formed and then evolved to their current orbits. But it turns out that, even though that's the basic scenario that we think is correct, nobody has yet been able to explain exactly how to get from that collision to the current configuration exactly. There's some, very interesting dynamical considerations that still haven't been worked out. But that's what we think is where all of these satellites came from that collision of 2, very large Kuiper Belt objects 4.6 billion years ago. Okay, so now let's get into the results from the mission. But before we do that, this is the best we could do from Earth. This is from Hubble. With the faint object camera, it's just a pixelated blob. But in fact, we could already tell from images like this that Pluto was pretty interesting. It actually has, when you watch it over a rotation period, which is 6.4 days, you can see spots like this white bright spot here, moves in and out as Pluto goes around in a 6.4-day cycle in synchronous rotation with Sharon. But this is why we do space missions. Who would have thought? Now, I have their orientation exactly the same. So you can see kind of a white area here. When you put a spacecraft there, this is in natural color, using the filters in the Ralph instrument and trying to compose an image in a way that would be most like what your eye would see. It's just kind of a yellowish image here. You get this huge region, looks like a heart. This is Pluto's infamous heart, okay, that became very famous during the flyby. This region of the heart, the left ventricle, is a huge slab of frozen molecular nitrogen, ice, okay? So that's what we're seeing. We wouldn't have known that without the New Horizons mission. And just a neat little factoid, the New Horizons flyby on July the 14th of 2015 was exactly 50 years after the very first spacecraft flyby of an extraterrestrial object, and that was Mariner 4 flying by Mars. Okay, exactly 50 years. So this is the lesson that we've learned from 50 years of space exploration. If you really want to learn something new and exciting about the objects in the solar system, you have to go there, and as this group very well knows. Okay, so we tried to put together this picture of what the eye would perceive, but of course, the eye isn't the greatest thing for picking out compositional contrast over the Pluto. So we actually have this color-enhanced image. It's not a cheat. This is, just using the three filters that we have, basically a blue, a green, and a red. It's really a near-infrared, a red, and a green, put together and stretched so that you can pick out different compositional units and just look at how diverse the landscape is here on Pluto. And because of the unusual geometry, and you'll see this a little bit better later, Pluto's pole is tilted over and it's actually underneath the ecliptic plane. And so we're flying into Pluto. The North Pole is actually right about here. The equator of Pluto is here. And around the equator of Pluto is this dark reddish belt, okay? And you have this giant slab of molecular nitrogen ice and then a whole bunch of other neat stuff. And I'm going to go through and talk about some of the landscape on Pluto's surface. But first, actually, before I start this movie, let me just tell you what this is. So what we're going to do is take real images from the spacecraft and put together a movie, and it's as if we're flying around the periphery of this big white ice sheet, which we informally call Sputnik Planitia. Okay, that's just an informal name, because we have so many features on the surface of Pluto, we had to give them names in order to be able to talk about things, among the science team. But this is just as imagine yourself, these are real images, these aren't artists or drawings around the periphery. Just look at this. Just flying around the edge, you've got this. It's basically Sputnik Planitia is a basin. Our best idea right now is that it's a giant impact basin. Probably a giant object hit Pluto. Not a giant object, something on the order of hundreds of kilometers across, hit Pluto about 4.5 billion years ago, between 4 and 4.5 billion years ago, created a big hole that then got filled in with this molecular nitrogen ice. Okay? Now let's step around and look at some of those regions around the periphery of Sputnik Planitia in greater detail. And I just want to bring out a couple of points. Okay, so first of all, and it's really a key point that we have frozen molecular nitrogen ice, because that is so highly volatile that you can actually have activity on Pluto, which is extremely cold. Okay? Pluto is only about 40 Kelvin, the surface temperature, 38 Kelvin to be exact on the sunward side. It's even colder on the other side, on the night side. Water ice is like a rock at Pluto's temperatures, but molecular nitrogen ice, we're close enough to the triple point that, in fact, molecular nitrogen ice acts on Pluto almost like water ice does on the Earth. So, in fact, you can have motion of the molecular nitrogen ice and solid-state convection taking place. And that's what we think we're seeing. We're seeing, you can see this little motion of the ice sheet across a barrier. You see it bending around the barrier and encroaching in the highlands around, actually, penetrating the highlands. So the ice sheet is actually moving just like a water ice crater on the Earth. Now look at these polygonal structures here. What we think is happening there is heat from below, and it's not much heat, is the leftover radioactive heating taking place that's heating up and then causing solid-state convection and upwelling and downwelling of that molecular nitrogen ice in Sputnik Planitia, just like a lava lamp would be. Okay? And you're seeing the upwelling and the downwelling, and we've actually done numerical modeling that suggests that this is very, very possible. Okay, now we go. This is on the western side of Sputnik Planitia. Look at this. You've got this jumble of giant water icebergs, basically. We think that water ice is like the bedrock of Pluto, but here you have this overturning of material bringing up these giant blocks of water ice that are essentially floating in the molecular nitrogen ice. And you actually see like a little leftover region here. It's like a lake on Pluto of molecular nitrogen ice where that wasn't happening. But these are, and here you can see the scale bar here, 80 kilometers. But these are giant, very chaotic region. It's reminiscent of similar things that we see on Europa, Jupiter's one of Jupiter's icy moons. On the other side, on the eastern side of Sputnik Planitia, we got these bladed terrains, which we now think are comprised mostly of molecular methane ice. Okay, the nitrogen ice is too weak to support structures like this, so we think it's molecular nitrogen ice, and it's almost unlike anything else we've seen throughout the solar system. These bladed terrains. We think we see something that's evidence of cryovolcanism, so material coming out of the interior of Pluto and flowing out onto the surface. This is our best example of that. And then in Sputnik Planitia, and as you come over on this is on the eastern side again, there's all these pits. In Sputnik Planitia, there are places where it looks like you've had sublimation of the molecular nitrogen ice and it becomes darker and it's a runaway effect. You get the molecular nitrogen ice subliming away, flowing over into the highlands, condensing, and then flowing back down into Sputnik Planitia. So very active rheology taking place near Sputnik Planitia. Okay, in addition to just doing the geomorphology from the imaging, the optical imaging, we actually have infrared spectral images of Pluto and Sharon. And here are 3 examples where we're focusing, we create image cubes, 256 different wavelengths, spanning from about 1 micron to almost 2.5 microns. And we can pick out individual absorptions in the infrared from water, methane, and molecular nitrogen. And this is particularly a very weak absorption. It's very hard to pull out, but you can see it's dominating Sputnik Planitia. You have some methane there as well, but most of that ice is molecular nitrogen. This is just a close-up of that dark red belt around Pluto's equator, which we think is probably heavy hydrocarbons, either produced on the surface after hydrocarbons have condensed out on the surface and been irradiated with cosmic rays, ultraviolet light at some point in Pluto's history, or raining out of hydrocarbons that have been produced in Pluto's atmosphere, then precipitating out onto the surface. And this is that image that was on the first slide. And like I said, when I saw this coming across my computer in early September, I just couldn't believe it. So there are a couple of remarkable things here. First of all, these are giant mountains. These are about the height of the Rocky Mountains in the United States. So several kilometers high. This is a panoramic view taken with the visible camera in the Ralph instrument, portion of the Ralph instrument. Just in showing you Sputnik Planitia here and all this remarkable landscape with the shadows of the sun is into the page. But what you see on the horizon is really remarkable. And this is something that we really didn't expect. This is not noise. These are bands, at least 20 different haze layers that you see on Pluto's horizon. So you get this forward scattering from haze particles in Pluto's atmosphere, creating this highly stratified haze layers. Okay, just a few minutes, to tell you about the occultation experiment again. This is the real geometry. The plane of the solar system is this that blue, plane here. The Earth and the Sun are down and to the right, and we flew through the Pluto system like this. And now, if you look at the actual data from the ALICE ultraviolet spectrograph as we flew through Sharon's shadow, not through the center, but through the edge, you see like a knife edge, okay? And it's really sharp because, as far as we can tell, Sharon does not have an atmosphere, okay? So it's very sharp. And that's to be contrasted with Pluto, where you see this very different kind of curve. You get this bending because now you're bending getting absorption of the light in the atmosphere of Pluto, in the upper atmosphere. And from measurements like this, we can pull out the composition of Pluto's upper atmosphere. And we get the temperature structure, shown over here to the right, and the pressure structure all the way down into the surface. Now, from stellar occultation measurements that have been made over many years now, you can only probe down to about 70 kilometers above Pluto's surface. This is the first time that we've been able to get all the way down to the surface and measure the surface. And Pluto's atmosphere at the surface is, by the way, almost exactly the same composition, dominated by molecular nitrogen, just like we have in this room, but it's about 100,000 times less dense. Okay? And this is the view of Pluto as we flew by, and this is not, this is the true color. It's blue. That haze layer is blue. We have blue skies on Pluto just like we have blue skies on the Earth. So the sun is into the page, and you can see, this is looking at a very high phase angle view. So if there was no atmosphere, you just see a little sliver of sunlit Pluto horizon. But now you see stuff all the way around, and that's that haze layer. This is our new view of Pluto. To compare it to the Hubble view that I showed you earlier, all the objects are resolved. We've transformed those pixelated blobs into real worlds with complexity and diversity. Not only Pluto and Sharon, but also the small objects we've actually resolved as well. Sharon, I could spend a whole nother talk talking about Sharon. The two remarkable things about Sharon is this huge chasm that wraps all the way around the center. What we think is happening there is that early in Sharon's history, 4.6 billion years ago, there was actually a water ocean underneath the surface that froze, and because of the freezing, it expanded and basically broke Sharon apart at the seams. The depth of this chasm is 10 kilometers deep in the deepest. Okay, there's a huge thing that runs all the way across. And then the other remarkable thing about Sharon that we did not know before is this dark red polar hood. And we just published a paper in Nature this month in which we have a proposal for how this was produced. Methane molecules have escaped from Pluto's atmosphere, and preferentially, cold trapped into on the coldest regions of Sharon, which are the poles, and then they're irradiated with ultraviolet light or cosmic rays or solar wind and transform. They break the bonds and form dark red material, which is what we see. And this is that chasm, and here's that scale that I was talking about, 7 miles deep at the deepest. Pluto and Sharon are two very different worlds. They're shown with exactly the same color intensity scale here. Pluto in general is much brighter, much more color diversity than Sharon. Here's our best family portrait of the small satellites. And this is kind of the best example of, it looks almost like comet Churyumov-Gerasimenko, two objects that came together producing a single object. That's what it looks like. The small moons, we've already got spectra of Nix and Hydra now. They got very deep water bands. We think that all 4 of those small satellites are basically just ice balls all the way through. And they were probably formed from the mantles of the 2 objects that collided to form the Pluto-Sharon system. And this is a little movie, if you could play it. The other remarkable thing is about the small moons. If you could hit the play button on this one, they're rotating much faster than synchronous with Pluto. Sharon rotates synchronously with Pluto, so the same face on Sharon and Pluto are always looking at each other, that 6.4-day period. But these little objects, and we don't see, oh, there they go. Especially Hydra, the one that's far out there, has a rotational period of only 10 hours. And it's out there with a rotational period around the barycenter of about 34 days. So nowhere near synchronous rotation, and their poles are tipped over into the plane, equatorial plane. So we have to explain all of these things. And just to finish up, Pluto, the results that we got, of course, were a big hit around the world last summer. Images of Pluto made the front pages of 450 papers around the world. Here is the iconic view of Pluto with its heart. I love Pluto. A huge amount. Of course, we're in the age of the instant media on Twitter and Facebook and so forth, and we've reached a lot of people. And so this was a good way to publicize the value of space science and space missions. I think a lot of people were engaged with what we were seeing last summer. Just to end, we're not finished yet with this mission. We're now about 3.5 AU past Pluto, but we have something else in our sights. We've already made the trajectory course maneuver to put us online to fly by another Kuiper Belt object that's in a completely different family from either Pluto, which is one of the so-called resonant Kuiper Belt objects, it's in a resonance, a 3-2 resonance with Neptune, orbital resonance, or one of the scattered Kuiper Belt objects, which is what comet 67P Churyumov-Gerasimenko is. So we've had missions now that have gone to 2 of those families of objects that are in those 2 different families. But the original Kuiper Belt, the one that probably formed in place, almost circular orbits, almost in the plane, the so-called cold classical Kuiper Belt objects, possibly the most pristine objects in the solar system, that's our next target. And right now it has only a number designation, 2014 MU69. It'll get a real name shortly, a more palatable name. But NASA gave us approval in July to fly an extended mission. And so on January the 1st, 2019, we'll make a close approach past this very primitive Kuiper Belt object. And who knows what we'll see. But with that, I'll just leave it with you. But stay tuned in a couple more years. Thank you.
Thank you, Hal, for a great talk. I think we've got maybe a few minutes for a couple of short questions. If there's anyone out there that has a question, come up to the microphone. Got a microphone.
Right there, right next to you.
Yes, during your talk you mentioned that Pluto is the first Kuiper Belt object that you've viewed up close. I've heard that same appellation given to Triton orbiting around
Triton,
Neptune.
yeah.
So which one is it?
Yeah, well, okay, so it's the first Kuiper Belt object observed in the Kuiper Belt, if you qualify it enough. But yeah, we do think that the most probable scenario for Triton is that it was captured, was a Kuiper Belt object, and is almost a twin of Pluto, and it got captured into orbit around Neptune. So that's true. And also we think that maybe some of the Trojan asteroids around Jupiter were also originally from the Kuiper Belt. And you could also say, for example, Comet Churyumov-Gerasimenko. But this is the first exploration of something actually in situ in the place where they were born.
All right, thanks.
Great presentation, thank you. Just one question. In terms of the Hubble telescope, why were they so off on the color to begin with? And why were all our previous estimates, it being gray, incorrect?
I couldn't really make out the question.
In terms of all of our previous expectations of Pluto, both from the Hubble Space Telescope and others, it was gray. However, New Horizons has shown that's not the case. And I was wondering why previous data indicated it was gray.
Okay, you were asking about whether or not the stuff that we learned from Hubble.
Why did we always used to think that Pluto was gray in color if it turns out from the New Horizons project that it's clearly a yellowy color?
I still can't make it out, I'm sorry. Maybe we can, I can talk to you after we finish. We're keeping everybody from dinner, but
There's a bad echo.
there's a bad echo, I think, up here. I'll come down to talk to you.
I was wondering, the extended mission, will it get as close to the next object as to Pluto?
Yeah, okay, so we're tentatively planning to go 4 times closer. So 4 times higher resolution, actually, than where we, so maybe, 3,000 kilometers from this primitive Kuiper Belt objects as opposed to 12,500 for Pluto. We're in the process of putting together the encounter scenario, and we'll be building that over the next 2 years. But that's that's our original baseline plan. And this object, by the way, is pretty small. It's probably only about 25 kilometers in diameter. So we want to get as close as possible to put as many pixels on that object as possible.
Thanks.
Hi, quick question here.
Yes.
So have you finished to download all the data from the flyby last year? Because when I saw the press conference, it was said that it was going to be like a long time to download all the data. So,
The funny thing is, everything we hear from over there, I can't hear very well, but I could hear him very well. I can't hear
okay, can you hear me?
I can hear a sound, but I can't make out the words.
Okay.
And so I'll come down also. I'll get both of you guys over here.
Okay, I asked from
Okay,
here. Yeah. Did you derive what is the makeup of Pluto overall? And you found nitrogen ice. And another question is, did you find organics also? And
Organics, yes. Okay, so we have seen, we already knew that ethane, for example, was present. Ethane ice and CO ice and methane ice were present on the surface. That dark red stuff, we have a lot of circumstantial evidence now that Dale Cruikshank at the NASA Ames has proposed, and he's produced in the lab with his collaborators at NASA Ames, what he calls a Pluto Tholin. If you remember, Carl Sagan and Bishun Kari in the Cornell lab used to produce these. They were trying to explain what they see in Titan's atmosphere, the large moon of Saturn. And by irradiating this mixture of these ices, and you could produce these organic materials. Well, we add a little extra nitrogen in the case of Pluto, and we produce these what are called now Pluto Tholins. And so we're pretty sure that these are heavy hydrocarbons, these dark red areas. One more maybe?
About one more.
Okay. Yeah.
Yeah.
Oh, well.
Let's see.
Hopefully we can understand.
Yeah.
Okay.
Thank you very much. Do you consider sooner or later to find any other materials we can find here in the Earth the Earth, but we can find them in Pluto. And I hope sooner or later, too, Pluto will be a normal planet for the Astronomical Society again.
Yes, Pluto is a planet. Will anybody agree? After seeing the pictures. But yeah, so we think that, basically as you get into the outer solar system, it's an organics factory out there because you have these exotic ices of methane that can condense out and are stable, ethane, methane, ammonia and molecular nitrogen, and then they get irradiated, breaking the bonds and creating these organic material. And some of that material rains in on the inner solar system, like the comets. That's where the short period comets come from. So they are bringing organic material into the inner solar system. So by studying, these objects in the Kuiper Belt, we're seeing, the factories, the hydrocarbon factories in place and trying to characterize them there. Yeah.
So that some people aren't going to miss the buses for the cultural night, let's give Hal a thank you again for a wonderful talk about a wonderful mission.
Thank you very much.
So thank you all for attending, and keep up with the mission. As Hal mentioned, January the 1st, 2019, we've got another target to see. Thank you.
La UDG te invita a participar en el Congreso Internacional de Astronáutica. Si eres docente o estudiante de esta casa de estudio y tu promedio es más de 80, puedes obtener una beca para asistir a este encuentro. Regístrate en el sitio de la Coordinación de Vinculación y Servicio Social. Universidad de Guadalajara invita.